Hello, welcome to the video on intermolecular forces. So first we're going to look at what these are, and then we're going to talk about how they relate to boiling point and melting points. Intermolecular forces are attractive forces that exist between molecules. Okay, so there are three types of forces. There are London. Okay, these are the weakest. And then there are dipole-dipole interactions, and then hydrogen bonding. So hydrogen bonding is the strongest of the three. Okay, and the strength of the force determines if it has a high or low melting point, and also if it's a solid, a liquid, or a gas. And we'll look at that separately in a different video. I want to remind you that intermolecular forces, these are not bonds. Okay, these are attractions between molecules, and I mentioned this in previous videos, but I want to go ahead and review this, that when we talk about attraction, we're talking about electron density, and we're talking about our magnet sort of scenario again, where positive attracts negative or negative attracts positive. That's what we're doing here. For London dispersion forces, these are also called van der Waal forces. These are very weak interactions that all of our covalent compounds have. Okay, and it's just due to the momentary change in electron density in a molecule. So in any molecule, the electron density will shift a little bit and cause this sort of a temporary dipole. Okay, it may benefit you to go back and watch my video on electronegativity if you've forgotten what polar means and what a polar covalent compound is. We'll try to review a little bit, but if you need to, you may want to go back and watch that. All right, so when you have this weak interaction between these temporary dipoles, a dipole is a difference in electronegativity. So you have a positive, partial positive, and a partial negative portion. All of our covalent compounds exhibit these, and this is what holds them together in solution or whatnot. But remember, our covalent compounds, these are compounds that are bonded and share electrons, typically nonmetals bonded to nonmetals. The larger the molecule is, the larger the attractive force and the stronger this London force is. So if you think about it, if a molecule is bigger, has a larger surface area, and so it can have more interaction. So the bigger it is, the stronger that intermolecular force. All right, here's two methane molecules. These are the same molecule, and as you notice, it's just sort of a shift in electron density. So we have a partial negative, so more electron density over here than over here. It's sort of just a temporary dipole, and in this molecule, electrons are shifted over here and leaving this side more partial positive. Okay, and so these are attracted to each other, okay, very weakly, but these methane molecules are attracted by this intermolecular London force. That's the weakest force of all. All right, dipole-dipole interactions are attractive forces between the permanent dipole, so this is not a temporary issue, of two polar molecules. Okay, how do we know if something's polar? So once again, this goes back to electronegativity and some of the previous videos you may want to watch, like I said, or rewatch them. Okay, and so if something's polar, it has a difference in electronegativity. Okay, so carbon and oxygen, this bond, this right here. Okay, carbon and oxygen have a fairly large difference in electronegativity. Okay, oxygen is much more electronegative than carbon, so it gets a partial negative charge for electrons, and the carbon a partial positive. And so these, here's the dipole-dipole interaction, okay, are held together by moderately strong attractive forces. Okay, this is formaldehyde, the molecule, and they're attracted, partial negative attracted to partial positive of another molecule, okay, to itself. And then if you look here, same thing. If you had a third molecule, okay, in reality there's hundreds to thousands of these molecules in a bottle or flask or wherever in your body or whatnot, okay? And so let's draw another one. So if our carbon's partial positive, so if we had another one, there would be partial negative. Okay, so dipole-dipoles, when you have a difference in electronegativity, okay, making one atom partially positive and one partially negative, and these are attracted. So these are polar molecules. So we talked extensively about this when we looked at polar covalent compounds. All right, the strongest force is the hydrogen bonding. Okay, I do not like this word, even though that's what it's called, but it's not a true bond. Okay, it is the strongest intermolecular force, but this is not a bond. Okay, bonds are ionic or covalent, right? Those are two types of bonds. Okay, we do not, hydrogen bonding is not a bond. That's why I don't like the name. It is still an intermolecular force. Okay, right here, those are bonds, right? These are covalent bonds that make up H2O. Okay, an intermolecular force is the force that's holding these two water molecules together, okay, or keeping them in solution or keeping them, okay, attracted to each other. Okay, this hydrogen bond is not a true bond. Okay, however, it is the strongest of the three types of intermolecular forces. And hydrogen bonding is the strongest because you have a hydrogen that's bonded to one of three highly electronegative atoms. So if you have a bigger difference in electronegativity, it makes it more polar, right? So you have a more polar molecule. Okay, so hydrogen bonded to an oxygen, that would be water, would be an example. Hydrogen bonded to nitrogen is also an example. So here's ammonia. It would hydrogen bond. Hydrogen bonded to fluorine. That's another example. Remember, fluorine is the most electronegative. Okay, so the difference here is going to be large, putting that partial negative on fluorine and partial positive on hydrogen because it's the least electronegative. So partial positive, partial negative. Okay, that partial negative goes on the more electronegative atom. Okay, and so how do they attract? Positive attracts to negative on a different molecule. So here in water we have partial negative, so it's attracted to the partial positive hydrogen. Okay, and of course there are thousands, millions of these hydrogen bonds occurring. We could keep drawing all over this page hydrogen bonds. Okay, so if we wanted to, let's draw another one. So here is partial positive, therefore it has to be attracted to partial negative. Negative and positive attract. So this right here would be a hydrogen bond. Same over here with HF. If it's attracted, partial negative has to be attracted to partial positive. So there would be hydrogen bond. Okay, so once again, intermolecular forces are forces between molecules. Okay, they're not bonds that hold atoms together. See, these are bonds that hold the atoms together. They are between molecules holding molecules together. Okay, and the strongest of these is hydrogen bonding. London's the weakest, then dipole-dipole. You have a polar compound, but when you have a very polar compound that has a hydrogen atom bonded to an oxygen, nitrogen, or fluorine, then it is hydrogen bonding interactions. A really neat example of this is in our DNA. The double helix is held together by hydrogen bonds. So this is what holds the double helix together in DNA. And so you can see here, you've got hydrogen bonding occurring between the oxygen and hydrogen, hydrogen and nitrogen, okay, the partial negative to the partial positive. All right, so here's a summary. London's the weakest. All molecules that exist have these. And some examples. Dipole-dipole, we have moderate strength, and they have a net dipole, meaning a partial positive, partial negative. That is permanent, not temporary. Okay, and hydrogen bonding is strong, and this is between hydrogen bonded to oxygen, nitrogen, or fluorine. One last thing that I really want to point out is that if you notice here, water has hydrogen bonding interactions, but it also is going to have dipole-dipole and London, right? All molecules have London interactions. Okay, and so if you find it, if it has hydrogen bonding, it also has dipole-dipole and London. Okay, and then if you look here, there's our formaldehyde. Okay. It does not exhibit hydrogen bonding, but it has dipole-dipole, which means it also has London. So all molecules have London. So that's going to be what you have to figure out is it polar or not, and does it have dipole-dipole and hydrogen bonding as well. All right, I hope this helps. Thank you.